Hello, class. This lesson we're going to learn how to describe regions with inequalities. So as a warm-up, I'd like you to graph the system of inequalities and answer the 3 questions. Then I'll show you my solutions. So here's my graph, and I've shaded this region here where the 2 inequalities overlap. So is a 1, 2 a solution? Yeah, it's in the shaded region. What about the point 1, 1? So it's not on the region. However, it does border that region, and it's on a solid line, so we do include it in the solution set. And this region is made out of the intersection of how many half planes? 2 half planes, one from the vertical line and one from the horizontal line. So same idea, graph the system of inequalities and answer the questions. So here's what my graph looks like. So is -2, 4 a solution? But while it is on a solid line, it does not border this region that's shaded from both inequalities, so it's not a solution. About 1, 3. So while it does border that shaded region, it is on a dashed line, and we exclude any point on a dashed line from the solution set. And once again, how many half planes is this made out of? 2 half planes. We get them from cutting diagonally, but they're still considered half planes. So now we'd like to use what we know about inequalities to describe a rectangular region. So you probably will get different answers than I do, and that's okay. But I'd like to name 3 points that are inside this region. So within this rectangle. Here are 3 possible solutions. What about 3 points that are on the boundary? On the boundary here. So points that lie on the actual sides of the rectangle. Here are 3 possible solutions. What if we wanted to describe every single point that's in the region or on the boundary? How can we describe all of them put together? Well, how can we describe all of their x coordinates? What's special about the x values here for any point we pick? Well, they're all greater than or equal to positive 1, and they're all less than or equal to 15. So we can describe them with this compound inequality. And what about the y coordinates? How can we describe them? Well, they're all greater than or equal to 2. They're all less than or equal to 7. So we can describe them with this inequality. If we put them together, these 2 compound inequalities describe the entire rectangular region and its boundary. So what's special about the coordinates that are on this left edge? What do they all have in common? Well, it's a vertical segment, so they all have the same x coordinate. So all the x coordinates are 1. What about the top side? What do they all have in common? Well, it's horizontal, so all of the y coordinates are equal, and they're all 7. And we have a rectangle, and what are some special properties we know a rectangle has? Well, we know it's a parallelogram, so the opposite sides are both parallel and congruent. We know it has 4 right angles, and we know the diagonals are congruent. So what if we wanted to find out how long one of the diagonals is? Well, let's work with this one. You can use the distance formula or Pythagorean theorem. They're the same thing. So if we subtract here, we figure out that the legs measure 14 and 5, and plug into Pythagorean theorem and take the square root, and we get about 14.9. Now, does it matter which of the 2 diagonals we use to figure out the length? No, it doesn't matter because they're both congruent. So you get the same answer even if you use the other diagonal. And can we name a point that is within the region, but is also on this diagonal here? So can we name a point that's on this diagonal? Well, there's a few different ways to do it. If we take the average of the x coordinates and the y coordinates, we find the midpoint. And we get 8, 4.5. We could also use the slope to find another point on that segment there. And the slope ends up being 5 over 14. But in order to change that into a usable slope, you would divide the numerator and denominator here by 5. So when we go up 1 in y, we go to the right 2.8 on x. So starting at our point 1, 2, if we follow that slope, we would end up with the point 3.83. So lots of ways to think about finding another point on that segment. So here we have this region, but it's unbounded to the right. It keeps going on and on forever. So what are 3 points that are in this region? Oh, lots of points you could name. There are 3 possible solutions. So how can we describe all the points in the region? Similar to what we did before with the rectangle. What can we say about the y values? What can we say about the x values? Well, the y values have a minimum of 1 and a maximum of 6. And the x values have a minimum of 0, and they just go on to the right without bounds, off to infinity. So let's write a system of inequalities that describes that. Now, another way to write a system of inequalities is as a set, because we're talking about a set of points here in a region. So I'm going to use set builder notation. And you might not have written it like this. This is one way to do it. But this says this is the set of all points, x, y, such that the x-coordinate is greater than or equal to 0, and the y-coordinate is greater than or equal to 1 and less than or equal to 6. So this set describes every single point that's in the region or on its boundary. And what's a horizontal line that passes through this region? There's a lot of horizontal lines that go through it. One possible one is y equals 4. 1, 2, 3, 4. Okay, similar idea here, but now we're talking about a triangular region. So graph the triangle, and let's see if we can answer these questions here. If you graphed it, you should end up with this triangle. And the region we get here is made by how many half planes? It's the intersection of 3 half planes, right? One from each side of the triangle. So you have to have 3 inequalities here. So what are the endpoints of this leftmost segment? So just this segment right here. Well, there's 0, 0, and 1, 3. So if we want to describe it, we have to figure out the equation of a line that contains those points. So what would the slope of that line be? That'll be 3, right? Of 3 to the right 1. And so what would an equation be? Well, you know, the y-intercept here is 0 because it passes through the origin. So just y equals 3x. And what about equations that contain the other 2 segments here? So you can write those equations, and I'll show you my solutions. So this one right here, that passes through the origin as well, so the y-intercept is 0, and the slope here is 1/2. Right, up 1 to the right 2. And this line is -2, x plus 5, right? Slope is -2, and if we extended this, we'd see that it passed through 5 on the y-axis. So what do we have to do here to describe the region, though? All we have right now are lines. We have to make them inequalities. So if we make them into inequalities, we see that we are, let me zoom out here, we are shading below the line, y equals 3x, so y is less than or equal to 3x. We're shading above the line, y equals 1/2 x, so that would be greater than or equal to. And we're shading below the line, y equals -2x plus 5, so less than or equal to. So make sure that your inequalities describe this inside region. And finally, same idea, but now we're going to talk about trapezoid. So graph this and see if you can describe the region with 4 different inequalities. So here's my picture and the 4 inequalities. Right, so the minimum y is 0, the maximum is 4. And if we figure out the equations of these diagonals here, these legs, we end up with these inequalities. So there's a little typo here. This one, this should have been less than or equal to as well, because we're shading below this line over here. Right, in this lesson, we learned how to describe regions with inequalities. Thank you for watching this video.